Okay, hi everybody. I'm so happy to meet you here. So today I'm gonna introduce. My name is Huan, and I'm gonna introduce you a new exciting project, surviving a disk apocalypse with the single-overlap declustered parity. Okay, for the past 10 years, the number of disk drives has been growing. This figure shows the number of disks incorporated into the Backblaze cloud service already reached more than 100K. And in 2017, the number of disks in HPC file systems approached 36K. So the increase in disks needs to increase the disk failures. Therefore, the failure burst become a reality. Let's review some anecdotes of the failure burst. 2009, a compromise solution using the multi-level redundancy to propose to handle the simultaneous failures. And 2010, Google reported a large number of failure bursts. 2017, copy set replication was proposed to handle the simultaneous failures. 2015, it pointed out that multiple disk failures might occur just in the same RAID group. And 2017, GitHub placed the data across the geographic data centers to avoid the catastrophic failures. And 2018, a layered redundancy was used to protect against the multiple disk failures. In this slide, I will show you some empirical failures. Okay, 2013, Facebook experienced up to 110 failures per day in the 3,000 node cluster. And in 2019, Lino experienced 432 disk failures within 24 hours in the MarFS system. And even in a single disk enclosure, 5 drive failures happened within less than 5 days in the Trinity system. And 2010, Google reported a large failure of burst containing 10 to 300 failures in the 1,000 to 7,000 node cluster. And in the 2004, Planet Lab experienced 4 failure events, and in the first half of the year, and in which 35 node failures occurred just in a few minutes. So I do think this example can show you, okay, we are studying the massive failures. That's scared. It's going to be a problem. So the Stanford researchers have identified some interview with the cloud operator. So they would like to minimize the probability of any data loss. So here, I'm going to propose a technical. Whenever minimizing the probability of data loss is the most important. Before we get started, let's review the erasure codes. Compared to the data replication, the erasure codes is just a storage-efficient redundant scheme. So the basic idea, we divide the original data into k data blocks, and then calculate m parity blocks. The parity is kind of redundancy information, so which comprise a stripe. Here in our 4+2 stripe, any 2 block missing, we can still use any other 4 block to reconstruct the data. But if they have more than 2 block missing, it will have data loss. So in the storage system, we have many of stripes, and each of them is independently encoded and distributed across the disks. Here, an important question is how we allocate the stripes across disks. One of the best ways is to use traditional RAID. Let's say we have 6 disks. We can divide it into 2 RAID groups. Additionally, each of which is configured with 2+1. Additionally, we have 1 dedicated spare drive. So the stripes can either put on the first RAID group or the last RAID group. The problem of this layout is the dedicated spare drive is idle during the normal operation. But the biggest problem is, let's say drive 1 fails. Then the stripes on drive 1 are degraded. Now the drive 2 and drive 3 have to read the reconstruction work node and write the reconstructed data into the dedicated spare drive. Here you can see, although we have 6 surviving drives, but just 2 of them participated in the reads, but 1 of them doing the writes. So essentially, the whole recovery process is bottlenecked by the single write. Therefore, the slow disk rebuild. This is the problem of RAID, but let's not forget the advantage of RAID. So it can either fail the first RAID group or the second RAID group. So rather than tolerating one failure, we can tolerate two failures. Now, let's look at what declass parity is and why we need it. Let's look at the dedicated spare drive. The first thing we notice, the dedicated spare drive is removed. Instead, every drive contributes part of space to be the distributed spare space. The 2+1 stripes are randomly distributed across the 7 disks. As you can see, the stripe 0 is spread across 1, 2, 4, and the stripe 1 is across disk 2, 3, 5. The big swing is, let's say, drive 1 failed. Then the stripes on drive 1 are degraded. As you can see, the reconstruction work node are available on all 16 drives. Therefore, every drive participated in read the reconstruction work node and write the reconstructed data back into the distributed spare space. Here, the read and write parallelism is made full use of, which greatly reduces the disk rebuild time. But if we have additional failure, then there's data loss. So compared to the traditional rate, declustered parity has a lower fault tolerance. In order to achieve the high fault tolerance and fast disk rebuild, let's take an example first. This is a 2+2 erasure coding in the 16 disk array. We can split the disks into stripesets. Each stripeset is a set of disks for placing a stripe. Therefore, each of our 2+2 stripe can put on just one stripeset. This means if they have more than 2 disk failure, so it will have data loss. But here, our 3 failures are distributed across the stripeset, so there's no data loss. With the random data distribution, you can see any combination of 4 disks could be a stripeset. Therefore, we have 16 choose 4 stripesets in total. That's 1,820 stripesets. So if we have any 3 failure, so it will definitely within a stripeset. Therefore, the probability of data loss is 100%. So as you can see, 1,820 stripesets, that's a lot. So we are going to propose a new scheme. We don't need so many stripesets. So this can give us, okay, because of that, we have a better solution to protect against the failures. This is a single overlap stripset. The basic idea is each pair of 2 disks just occur in one stripset. The goal is to achieve the declustered data layout with the minimum number of stripsets, but we don't sacrifice the rebuild performance. As we can see in this table, just 20 stripesets are needed to construct the declustered layout. So let's check the stripset for each disk. For example, disk 4. It comprises the first stripset with disk 1, 2, 3. The second stripset with disk 5, 11, 14. This is the third one, fourth one. And as we can see, the disk 4 participates in 5 stripesets, but none of our disks are overlapped here. So it meets our requirement. So at most 1 overlap for any 2 stripesets. Here, these 5 stripesets just overlap at the disk 4, and this is true for every disk. So if disk 4 fails, then the remaining 15 disks can help to recover, which achieves the same rebuild performance as the declustered parity. And this is also true for every disk. That's why we call it single-overlap declustered parity, or SODP for short. Let's continue with the multiple disk failures in SODP. If disk 1, 2, 5, 7, 11 fail simultaneously, surely we have data loss because we are using 2+2. But let's look at the actually stripset. As you can see, just the stripset in red are affected. There's no more than 2 failures in the stripset. There's no data loss, even in the presence of 5 disk failures, which achieves higher reliability than the declustered parity. So I already showed you SODP is able to tolerate more failures. I have a lot of results to show you. Instead, I will show you one important result and dig into how to implement SODP. Look at this graph. Along the bottom, this is a percent of failures. We vary that from 0 to 1 of the total disk failure, we're going to fill them as a burst over 24 hours. The y-axis is the probability of data loss. As you can see, with the fully declustered parity, the DP, you can see the gold line. So in 1% of failures, it has 30% probability of data loss, and which is similar to the D rate. And you can actually see rate is in the middle. This is very interesting. Why is rate better than the declustered parity? Because of bursting nature of the failures. Therefore, being able to tolerate more failures is more important than being able to rebuild quickly. What's the base of all is SODP. SODP can do both. It can tolerate more failures and rebuild quickly. So it's not making a trade-off either or. They can do both. For that reason, compared to the traditional rate, we can reduce the probability of data loss by almost 10 times. And compared to the traditional declustered parity, we have almost 30 times lower probability of data loss. I have more results analysis to show you, but I don't have enough time. So I'm going to transition from talking about the results to talking about our SODP algorithm. So it comprises of 3 parts: the column Stripesets, column-based Stripesets, row-column Stripesets, and row-based Stripesets. Here, I'm going to explain with a small example. You can kind of understand it, but that's complicated enough. But you might need to hear twice to be able to get it. So I apologize, I cannot find a way to make it simpler. But sometimes good things are not simple. So here we organize our 16 disks into a disk matrix, where the number of rows is equal to the size of one Stripeset, and the number of columns is decided by the total number of disks. Since we use 2 plus 2, so we have 4 rows, 1, 2, 3, 4. And we have 4 columns, which can describe as A, B, C, D. First, let's look at the column Stripeset. Since the number of rows is equal to the size of one Stripeset, therefore, each column could be a Stripeset. So the disk 1, 5, 9, 13 comprise the first Stripeset. And disk 2, 6, 10, 14 comprise the second Stripeset. And here is the last 2 column Stripeset. Now, let's take a look at row column Stripeset. The basic idea is to comprise Stripeset using disks from the different rows and different columns. I think the most simple and straightforward way is to use the diagonal disks. Here, it comprises Stripeset 1, 6, 11, 16. The diagonal disk can be represented as 1A, 2B, 3C, 4D. So it can be further simplified as a column relative position array, 1, 2, 3, 4. As we can see here, one Stripeset corresponds to one position array. So to generate more Stripeset, it's better to have more position arrays. What we could do is to permutation shuffle. The basic idea is we swap any pair of 2 positions. For example, if we swap 1 and 2, 4 and 3, so the new position array 2, 1, 4, 3 can generate a new Stripeset 5, 2, 15, 12. And we can do more swaps, but we have to choose a different position to swap. Here, we swap 1, 3, 2, and 4, so which correspond to a new Stripeset. We can continue the swapping algorithm until find all the remaining position arrays. Here, 4, 3, 2, 1 correspond to the Stripeset 13, 10, 7, and 4. Yes. As you can see, in our 4 position arrays, each column have the different row ID, which correspond to 4 non-overlapped Stripesets that cover all 16 disks. So what we could do next is fix the first position and rotate the remaining position. So what will happen is the first position is still 1, 2, 3, 4, but the remaining position are rotated. Here, 2, 3, 4 become 3, 4, 2. As you can see, the 4 new position array correspond to 4 new Stripesets. These are still non-overlapped, but they are just single overlap with the previous Stripeset. And we can continue fix the first position and rotate the remaining position. So these 4 new position array have 4 new Stripesets. So they are still non-overlapped and satisfy the single overlap property. Here, I think this example, everything is perfect and it's very easy to explain. But I just want to point out, so we choose a diagonal position array, we do the swap permutation, and then we do the rotation. So this simple swap permutation and a rotate approach does not work for all cases. For example, if we have the number of Stripesets is the odd number, for example, we have 1, 2, 3, 4, 5, 6, 7 rows. So what do we know? We could do 1 or 2 for the second position array, 1, 3 for the third position array, and so on. But for the remaining positions, how to swap, we have a lot of choices, but we just need one choice for each position array. Let's look at the second position array. We have to generate the remaining 5 position array. Now let's swap 3 and 6 first. Okay, if we apply the rotation here, let's see, it will have double overlap with the diagonal position array. So this is bad. We don't want double overlap, just a single overlap. So how to fix that? Let's look at, how to fix that? Let's look at the primary reason first. As you can see, our process is fix the first position and rotate the remaining positions. So we can put the first position in top and draw a circle for the remaining positions. So the distance between the positions is called rotated distance. So the rotated distance from 3 to 6 is 2, because it have to go through 4 and 5, so the rotated distance is 2. And likewise, we generate another different circle for the second position array. Here, our rotated distance from 3 to 6 is still 2. It have to go through x and 1 to 6, like this. So due to that, so that's why we have the double overlap. So therefore, we have to add a constraint. So the rotated distance before and after swapping cannot be equal. With this constraint, we can 3 and 6 cannot be swapped. 4 and 7 cannot be swapped. So with this constraint, we can avoid the multiple overlaps with the previous diagonal position arrays. How to avoid the multiple overlaps with other later position array? Here, because our 2, 3, 4, 5, 7, 6, we are unclear how to swap. So we draw a circle like this, clockwise. And then if we swap 7 and 5 in the second position array, we can never do this swap again in other later position array. So how could we prevent ourselves performing this swap? We can record the swap history, but that's not efficient. So what we could do is we can fill in the second position array first. We swap 3 and 4 and 6 here. Now we already have the second position array. So what we're going to do is we will walk away the whole position array, increment the positions. At the same time, we increment across this circle. Let's see what happens. 4, 5, 6, 7, 2, 3. Notice we just increase the position along the diagonal direction. And here, 3, 4, 5, 6, 7, 2. And this is a final result. This is a final result. Let's check the overlaps with the second position array and the other position array. We choose the fourth position array, okay? So if we apply the rotation in the fourth position array, we can see, because for the second and fourth position array, the 6 is followed by 5 in both of them. So as we can see, after applying the rotation, it will eventually overlap with the second position array. So we still have double overlap. This is not what we want. So how could we fix this? So as we can see, in the 6 and 5 in the fourth position array is derived from the 4 and 3 in the second position array. And the rotated distance from 4 and 3 is you go through 5, 6, 7, 2. So the rotated distance is 4. But the original rotated distance from 6 to 5, you have to go through 7, 2, 3, 4. It's still 4. That's why the derived position array have the double overlap with the previous, the second position array. So we have to add another constraint, which means we should guarantee the distinct rotated distance in the second position array. With this, so if we swap 3 and 4, so we cannot swap 5 and 6, 6 and 7 like this. And we swap 3 and 5, so no swap for the 4 and 6. So with this constraint, we can avoid the multiple overlaps from the second position array to the other later position arrays. So if we apply these two position array, I will show you example how it works. So in the second position array, we can swap 3 and 4 because the remaining 5 positions are unclear. So we have 3 choices. But what we notice is 4 to 3, 6 to 5. So these rotate distance are the same. So all of them violate the constraint 2. So we can swap 3 and 5. So we still have 3 choices. Here you can see the rotate distance from 5 to 6, 3 to 4. Okay. Yes, both of them violate the constraint 2. And in the second choice, we can see we swap 4 and 7, which violates the first constraint. And if we swap 3 and 7, and still 3 choices, now we can see the first one does not violate both of the constraints. It's the result we want. Of course, you can continue this process. You will find more feasible solution, but I will stop here. So the most difficult part already finished. We already introduced the column-based strap set, row-column strap set. Now let's look at how we generated a row-based strap set. Since in our disk matrix, each row just have 5 strap sets, which is the size of the strap set. So each row could be a strap set. In total, we have 4 row-based strap sets. Okay. This is the 20th strap set I introduced in the beginning. Just 20 strap set, we can achieve the declustered data layout. Of course, you may see, if each row has more than 4 disks, for example, if we have 4 disks, so it will need to another case. So some disk will, each disk will overlap with a single overlap with some disks, but 0 overlap with other disks. This is what we discuss next time. This is fractional overlap declustered parity. Let's review the SODP. First, the column-based strap set. Yes, this is simple. And for the row column strap set, first we choose the diagonal position array and do the swap permutation to generate more position array. And then we do the rotation until they have no rotation anymore. And meanwhile, we should apply the first constraint to guarantee the single overlap with the previous diagonal position array, and apply the constraint 2 to guarantee single overlap with other later position array. And later is row-based strap set. In conclusion, our SODP highlights the overlooked fault tolerance of the declustered parity and guarantee the same disk rebuild performance. So in our next presentation, I will show you our fractional overlap declustered parity, FODP. Thank you.
Questions? Let's go to the mic.
Thank you for your presentation. What is the minimal number of disks a system needs to have to successfully use this approach?
Okay, currently based on our solution, if the strap set is n, we should have n squares disk in total.
Okay, thank you.
Any more questions? Thanks to our speaker again.